All right, torque. Very important concept. It is the equivalent to force for translational. In fact, it involves force. But there's more to it than that. And I'll give you this example. It's to me, it's the best way I can explain what torque is and why it's the same and why it's different. Why it's different. I want you to imagine a top view of a door. So here's the hinge, and here's the door itself. All right, and the handle will be out here. Except this is one of those doors that doesn't really have a clear handle, like the one at like a Wawa or some kind of a convenience store. And the hinge may not, we know it's here, but when you're leaving the store, it's an unfamiliar store to you. So we're painting a picture here. You stop at some, some convenience store, and you're on a road trip, and you go to leave the place, and as you leave, you push here on the door, expecting it to just swing open. You know you've done it. You know you've done it. And you try to play it off. You try to look like you're being cool about it, right? But you are struggling to open that door, right? Picture it. Okay? When you push on the wrong side of the door, it's hard to open the door. So you either like knuckle down and push really hard, or you gradually slide yourself so your force is out here away from the hinge. Why do you do that? Why can't we open the door here just as easily as we can here? It's because when you open a door, unless you're a gorilla and you rip it off the hinges and throw it, that's translational motion. When you open a door, it's all about rotation. You are trying to change that state of rotation. The door is not rotating. You want to accelerate it, in this case, from this top view, counterclockwise. So, where do you push? Well, if you don't want to have to push really, really hard, you're weak like me, you want to push as far away from your axis, right? This is the hinge is your important point here, your axis of rotation. I'll even put that in darker letters. Axis of rotation. Rotation. You get the idea. You want to push as far away as you can to get the maximum torque. So pushing with a little force here can do the same thing as pushing with a very large force here. Why? Because, and here it is, torque is not just the force you apply. It is the force times the distance away from the axis. Now, this is why I should have looked it up beforehand. I can't recall if they use L or R in your equation sheet. Let me look. Okay, so I went and checked the equation sheet, and they use R. And in fact, I'll write it exactly like you would see it on the equation sheet. So it matters not only how hard you push, but where you push. This R is the distance from the axis. So for this force, that would be R. So we'll call this force 1. This would be R1. And R2 would be this distance and this force. We'll call it force 2. And you could have two very different forces, right? A small one and a large one, produce the same torque because one of them has a small r and the other one has a large r. So that's the fundamental difference, is that it's not just how hard you push, it's where you push, and where is in relation to the axis of rotation. The farther away you are from the axis, the easier it is to spin something. So if you had a bicycle wheel, it was sitting there like on a peg or something, and you wanted to spin it, you wouldn't grab one of the spokes here and try to spin it. If you wanted it to be easy, you grab it on the edge and you spin it. All right, because you'd have to do a big force here just to get it to start. Here, a smaller force would do, but you'd get the same torque. So what about this perpendicular and what about this sine? Well, they're connected to each other. What that means is that when you go to push on your door, you might push with your hand like this. Well, that means part of your force through friction is pushing away from the axis and doesn't do a damn thing in terms of rotating it. The only part that matters, the only component of your force that matters, in fact, here, let me draw it this way so it's clear. So here's our door, and you push on it like that or pull on it, whatever, and you have, so let's say your force, we'll say it extends like this. So that's your force. It has this horizontal component that is doing nothing to rotate the door. I mean, it's like walking up to a door and pulling on it this way. That's never going to open a door. You might pull it off the hinges if you're strong enough, but it isn't going to open the door. The only component that matters is the component that's perpendicular to the door. So here would be the angle of your force, theta, and the sign will give you the perpendicular component. That's why the sign is there and this symbol is there. So it's interesting, if you, just a side note, force times distance is really the same thing, right? It's force times a distance. Force times a distance. But this work, and the difference between work and torque is that this is the parallel component between them. So if you were dragging the door across the room, then yeah, this is the component you want. But if you, the perpendicular component, does nothing for work, but does cause things to spin if they have an axis. So the units are interestingly the same. Newton meter, although you would never write this as a joule, whereas this you could. You would write Newton meter, period, end of story. There's your units on torque. So the big idea with torque is it's where you push and how hard you push combined. That's what torque is.